Okay, so he's running at 5 meters per second, and he throws a football with a velocity of 25 meters per second at an angle 40 degrees with the horizontal. So there are two vectors here. And it says, what is the resultant speed and direction of the pass? This is like what we did on the worksheet, where if you have two vectors and you want to find the resultant, you take one vector and then you put the second vector at the continuation of it. So the first vector is he is running forward at 5 meters per second. So that's his vector here, 5 meters per second. And the other vector is the ball is going at 25 meters per second at an angle of 40 degrees with the horizontal. So there, and that's a little bit of a longer vector because it's 5 times longer, okay? Now you don't necessarily have to draw it that much to scale every single time, but it helps in the beginning to see it, okay? So I'm going to call this vector P for the player, and I'll call this vector B for the ball. The magnitude of that vector is 25 meters per second, and here it makes an angle of 40 degrees with the horizontal. So what we're doing essentially is now we want to find the magnitude and the direction of the resultant. Here is the resultant. Okay, this is the resultant, P plus B. Except now we're going to do it mathematically. So we have to write the two vectors, P and B, in component form. Well, if I have vector P is strictly horizontal. That means it doesn't have a vertical component. So its components are 5 in the positive x direction, comma 0 in the y direction. Okay? Now for B. B has to be resolved into components. So if you look at its components, you have a horizontal and a vertical. The horizontal component here is the side that's adjacent to the 40-degree angle, and adjacent means cosine. So you always do magnitude times cosine, magnitude times sine. If it's the vector, if it's the component that's adjacent to the angle, then it's 25 cosine 40, and this y component is 25 sine 40 because it's the opposite side. Now, direction. The x vector is pointing in the positive direction, so is the y vector, so both of these are positive. So that's my B vector in component form. Now, what I need is the resultant, meaning I need P plus B. For this, you're just going to add components, just straight components. So it's 5 plus 25 cosine 40, comma 25 sine 40. So how much is 5 plus 25 cosine 40? 21.15, comma, how much is the sine? 24.15? And how about the sine? 25 sine 40. Okay? That's the component form. Now, I need the magnitude. P plus B's magnitude is the square root of 24.15 squared plus 16.1 squared. Okay, so how much is that when you take a square root? Meters per second. So that's the magnitude. That means he threw the ball at 25 meters per second. But because he initially was also moving at 5 meters per second, the ball is moving at 29 meters per second, even though he threw it at 25. Okay? Had he been standing still and thrown it, the ball would just have been moving at 25. But now, because he was running, it's moving faster. And what about the angle? If this is the resultant vector here, the angle is the angle from the horizontal to the vector. Okay? And there's only one way to find that, and it's that tangent of theta is y over x. So tangent of theta is 16.1 over 24.15. So theta is the inverse tangent of 16.1 over 24.15. And what does that give us? How much? 33.7? Okay. That's the angle of, that's the direction of the resultant vector. Okay? 33.7 degrees. So even though he threw it up at 40 degrees, it's not flying at 40 degrees. It's flying at 33.7 because he was also going horizontally forward. Okay? All right, so let's move on to section 3. And here what we have is, we're going to talk about dot products. So here's what a dot product is. Suppose you have two vectors, A and B, which are, joined like this, A at the tail of A at the tail of B. Now, suppose you shine a light on A, like this, okay? If you shine a light on A, then a shadow of A will be cast on B, right? And here is the shadow right there. That's the shadow. Well, in math, we don't call it a shadow. We call it a projection. In fact, instead of calling it the shadow of A, we call it the projection of A onto B. Okay? Projection of A onto B. Now, so we shine a light. There is a shadow. Suppose we now measure the length of the shadow. Okay? So we measure the length of the shadow with a ruler. And then we measure the length of the vector B, okay, with a ruler again. Okay? And for fun, if we multiply together those two lengths, what we have is a dot product. Okay? So that's the dot product. Now, no. Because we now know how to find magnitudes, right? Okay, now, if you measure the length of the shadow or the length of the projection with a ruler, is that number that you get a vector or a scalar quantity? It's a scalar because you just measured the length with a ruler, okay? Now, if you measure the length of vector B with a ruler, is that a vector or a scalar quantity? That's a scalar as well. That means the dot product is a scalar quantity because all the dot product is a product of two regular old numbers. Okay? All right. So there is a formula to finding the dot product, and it's actually if you have A in component form and if you have B in component form, then if you want to find A dot B, all you do is A1 B1 plus A2 B2. It's just like if you had a row and a column matrix. Just like that. In fact, what are vectors? Just row or column matrices. That's all right. All that Rubik's Cube algorithm, matrices. Yeah. Okay. So, okay. So we're going to derive this formula for the dot product. Okay? We're going to derive the formula for the dot product. using the distance for BA. All right? So here you have two angles. Here you have 2 points, B and A. How do we find the distance between 2 points? Distance formula. So, if I wanted to find the distance between B and A, that's like the magnitude of BA, right? So, it would have to be the square root of A1 minus B1 squared plus A2 minus B2 squared. Right? Now, what if I squared both sides? Then the magnitude of BA squared is just A1 minus B1 squared plus A2 minus B2 squared. Now, let's FOIL this. We get A1 minus 2A1B1 plus B1 squared plus A2 squared minus 2A2B2 plus B2 squared. I'm foiling. A plus B squared is A squared plus 2AB plus B squared. Okay, now what I'm going to do is collect like terms. So let's collect these terms. A1 squared plus A2 squared. Why am I combining that way? I'll tell you in a minute. A1 squared plus A2 squared plus B1 squared plus B2 squared. Now, the other ones are minus, I'm going to factor out the minus, okay? So it'll be 2A1B1 plus 2A2B2. Okay? All right. Now, what have we done really? Let's go back to our original diagram. Okay? Here is vector A, and here is vector A in component form. Okay? How would we find the magnitude of vector A? How would you find the magnitude? The square root of A1 squared plus A2 squared. Now, what if I squared it? Just because I don't like the square roots. Then A squared is A1 squared plus A2 squared. Okay? So then what is this really? It's the magnitude of A squared. So then what's the other one in the blue? The magnitude of B squared. Now, look at this like your Pythagoras. Wait. Look at this like your Pythagoras. Look at this triangle. What's the Pythagorean theorem? Magnitude of A squared plus magnitude of B squared is magnitude of BA squared, except you've got that, ugly stuff over there. All right? So this sort of ruins it. Now, what does all this mean, though? So this is the Pythagorean theorem right here. Except if only this was equal to 0. Okay? Well, let's think about this. When does the Pythagorean theorem hold? For what type of triangle? For a right triangle. And if you had a right triangle, and if A and B were really perpendicular to each other, and if you were to shine a light on A, so if I'm standing perpendicular to the ground, and the sun is directly above me and shines on top of my head, how much of my shadow is on the ground?
None.
None of it. So if these really were perpendicular, there is no shadow. That means this would be 0. So the Pythagorean theorem holds for the right triangle. Okay? The rest of it is the part for the shadow. So that's the dot product. That's where it comes from. Okay? So let me tell you again. If A and B were perpendicular, then there would be no shadow. And this part here would be 0, and the Pythagorean theorem would hold here. Okay? So the part here is, that's extra, that's the shadow part. So that's the dot product. That's how much of a shadow is falling on B if you shine a light on it. Okay? The dot product is this, A1, B1 plus A2, B2. The 2's go away. Okay? Because you just divide them out. All right, so that brings us to orthogonal vectors. Now, okay, so if you go, what does the orthodontist do to your teeth? He makes them what?
Straight.
He makes them straight, right? The orthodontist makes your teeth straight. And if you go to like, and what's orthopedics all about? It's all about making your spine straight. So this word ortho, and like the ortho mattresses and whatever, it's all about, you know, making your spine straight. So ortho means straight. Orthogonal then means perpendicular. So orthogonal vectors means perpendicular vectors. Straight. Like if there's, you know, it's a straight angle. Okay. So if the angle between two vectors is 90, and it's just like what we talked about before, and if I shine a light onto one of the vectors, there is 0 shadow onto the other vector. So if the angle is 90, then the dot product will be 0 because there is no shadow, and that means the vectors are orthogonal. So vectors A and B are orthogonal if A dot B is 0. All right, so let's find the dot product here. You'll find that the...
Wait, is that what we write on the test case?
Yeah, yes.
I still don't completely understand what the dot product is.
The dot product is if there is a shadow, like if you have two vectors, here, like this, and if you were to draw the components on one vector onto the other, like this, the components, it's the component of this vector A that falls along the vector B. That's the dot product. Okay? So, let's find the dot product here. You'll find it's really straightforward. So, U dot V is, now remember it's a scalar, so it's going to be negative 3 times 3 plus 4 times 6. So this is negative 9 plus 24. So how much is U dot V? 15. Okay? It's like multiplying matrices. It's just like if this was a row matrix and this was a column matrix. Okay? All right, so let's find U dot V here. It's 2 times negative 14 plus 7 times 4. Negative 28 plus 28 is 0, so these are orthogonal. Huh? Mm-hmm. Sometimes the test will say, like, are these two vectors orthogonal? And you have to know. That means that they're not. That means the angle between them is something other than 90. Okay? Okay, so because this is a scalar, right? A dot product is a scalar, then the commutative property applies. the distributive property applies even for regular vectors. You can, like, scalar multiplication will work. 0 dot u is 0. And u dot u is just the magnitude of u squared. And we'll do more with that last one, like right now. Okay? All right. Suppose you have a vector A. And you clone that vector A here. Now, you shine a light on this vector A. How much of the vector A on top, how much of that shadow will be on the vector A on the bottom? All of it. Okay? So, the amount of vector A that will be on vector A is the entire length of vector A, which is the magnitude of vector A. Right? So, so if you wanted to do A dot A, what we want is how much of this vector is going to be a shadow on this vector. Well, the entire length of it. So if you did A dot A, it's really the magnitude. Okay? So the magnitude of A is the square root of A dot A. What do I mean by that? So use the dot product to find the magnitude of A. So it's like, yeah, so we're going to do A dot A, right, in a square root. So it's just going to be -6 times -6 plus 5 times 5 in a square root, which is 36 plus 25, 51. 61? Oh, 25, sorry. Right. Okay. Okay. So, what about the angle between two vectors? All right. So, how did we find, what was A dot B? A dot B was the length of the shadow of A. Can I just stop for a minute and say, like, how much I love this stuff? Like, you just have, like, I can't even explain. Like, there are no words in the English language, and I have, like, a good knowledge of words of the English language, and there's just, like, I can't even explain this.
Can I stop and explain how exhausted?
When did this conversation turn about you? Okay, so A dot B is just the length of the shadow of A times the length of B. Okay? Length of B, magnitude of B, you know, just those words should be interchangeable. Okay? They are interchangeable. Okay, so this is the length of the shadow here. But we also know that if we took vector A and if we resolved vector A into its components, then this would be like the horizontal component of A, right? That's the cosine. So now this is the component of A that's adjacent to the angle. Adjacent means cosine. So the length of this is A cosine theta. Okay? Now, let's put that in here. A dot B, length of shadow of A. I don't know what that is. That's just A cosine theta. All right, so this now, A dot B is equal to A cosine theta. So it's the length of the shadow of A times what? The length of B, which is the magnitude of B. And here, this was the magnitude of A times cosine theta. Okay? And now, this is starting to look like something. To clean this up, yeah. To clean this up, we write it like this. So A dot B is equal to the magnitude of A times the magnitude of B times cosine theta. Okay? And you could just be going around saying this all day long. A dot B is AB cosine theta. Everybody knows that, and now you know that as well. Okay? So that's what it is, exactly. So that's all it is. It's just a projection. It's just a component of A that falls onto B. Okay? Now, can we solve this for the cosine of theta? So cosine of theta is what? It's A dot B divided by the magnitude of A times the magnitude of B. And with that, you can find the angle between any two vectors. Okay? All right. And it's very elegantly presented here.
Wait.
It does make sense.
So wait. So how would we? Okay, I'm just asking. So if you were to plug in. Wait. Never mind.
Let's plug stuff in the next example, and you'll see.
Never
Okay?
mind. No, I'm wrong.
Okay. Okay, so look. Let's plot this for a minute. Let's just take some time to do this. You have a vector u, and its components are 1 and -4. That means you go over 1 and down 4 units, right? Here, so that's your vector u. Okay, and I admit it's not like completely accurate, but it's close enough. Then you have your vector v. Okay? So where is v? You go across 2 and 6 up. Okay? All right, give me 1 second. Let me see. All right, so let's find the angle between them then. For that, first I need a couple of parts to this. So first I need to find u dot v. Come on. All right, so the formula for cosine of theta is u dot v over magnitude of u, magnitude of v. So what I'm going to do is find each of those separately and then just plug them in. All right, that's the best way to do it. So u dot v is equal to 1 times 2 plus -4 times 6. How much is that? -22, right? All right, now I need magnitude of u, which is just the square root of 1 squared plus 4 squared. So magnitude of u is root 17. And then I need magnitude of v, 4 plus 36, which is the square root of 40, which is 2 root 10. Okay, let's plug all this in. U dot v was -22 over the square root of 17 times 2 root 10, which is equal to -11 over the square root of 170. So how much is theta? It's the inverse cosine of -11 over the square root of 170. So how much is that? Anybody? 147.5 degrees. That's that angle here.
Oh my god.
Do you see that? That's the angle that we found. Okay?
So cool.
All right? It is kind of cool. All this using the projection. Just the length of the shadow that one casts on the other gives us that angle. It's really something amazing. Huh?
It's not about the shadow.
It's the component. It's the component.
It's like one shines the light into the other so that we can create a solution using the help that we get from one another.
147.5. Okay. All right. So what we talked about before was A dot B was the projection, right, times the magnitude of B, right? That's what we've been talking about. So now if I just solve for the projection, then it's A dot B over the magnitude of B here. Okay? Now, this we said was a scalar quantity. A dot B, that's a scalar. Magnitude of B, that's a scalar. So now the projection is just a scalar. I'm just saying that that component on B, that shadow on B, has a length of 12 centimeters. That's just a scalar quantity. What if we wanted to give it a direction? Okay, so technically, it's the shadow that's on B. Okay, so in what direction is that going? It's going at the same direction as B, right? Remember what we talked about before? If this was vector B, and this was the vector A, and now here is the projection, okay? It's going in the same direction as B, yes? So now, no. But your shadow is always in the direction of the ground, isn't it? Is your shadow ever like standing up? But that's because you have like, okay, so that's just optics now. That's just optics. Right. There are no obstacles. Yeah. Okay. Now, so we want to give it a direction, right? Now, how do we specify a direction? Well, that's where unit vectors come in. Last time we talked about unit vectors. All unit vectors are something to give it a direction. All right? So now if we have the magnitude, okay, and we want to give it a direction, we want to give it the same direction as B. That means I have to multiply it by the unit vector of B. Okay? So multiply by the unit vector of B. Meaning, here is my projection. This is the length of my projection. Okay? What was unit vector? You take the vector and you divide by its magnitude, right? This is the unit vector for B. If I multiply those two together, then I give my shadow its direction. Okay? So look, I'm going to multiply the first thing I circled times the second thing I circled. All right? And what do we have here? A dot B over magnitude times magnitude, magnitude squared times that. So if you write that down, this is how it looks. It's A dot B over the magnitude of B squared times B. Okay? Now let's do one. Yeah.
What is the A times B over magnitude of B?
Magnitude of B, that's the projection. That's the length of the projection. That's the length.
B over magnitude.
This first thing I've circled, that's the Length of the projection. And now this is its direction. So this is the length, and this is the direction. Okay? So let's do that now. And then I'll, okay, so let me do this one and then I'll draw this next time. Okay. Find the projection of u onto v. So this is what we have to find now. Okay? So projection of u onto v is equal to u dot v over the magnitude of v squared times vector v. Okay, so let me find u dot v first. Negative 1 times 4 plus 5 times 6. Negative 4 plus 30. What is that? Negative 26. Positive 26. And then I need the magnitude of v, which is the square root of 16 plus 36. Is that right? So how much is that? 52, right? But I want that squared. So that's just plain old 52. So now let me just plug that in. What I have is u dot v, which is 26, over 52, times the vector v in all its glory right there. Okay? So now this is 1/2 times 4, 6. So the projection is 2, 3. Okay. Now, I'm going to call this W. Because I'm going to use it in the next problem. Why W? Because I had U, V, and now this is going to be W. Okay? Now here it says write U as the sum of two orthogonal vectors, one of which is the projection of U onto V. Well, I just labeled projection of U onto V as W. So I want U to be the sum of two vectors, one of which is W. So W plus some other vector Z. Okay? Right, well, it will be, as it turns out. So look at what we're going to do now. So what is Z? If you subtract W from both sides, it's just U minus W. So Z is U, which was what? Negative 1, 5 in the previous part. Minus, what's W? 2, 3. So what's Z now? Minus 3 and 2.
So then you write it as 2, 3 plus.
Right, so now you say U, what was U? Negative 1, 5 is equal to 2, 3 plus negative 3, 2. So just for fun, find the dot product of these two.
Just for fun. Wait a minute, how are they so hard?
Find the dot product. Find the dot product.
The dot product is 8 times b, so it's going
Oh,
to be, and they're orthogonal, so it's going to be 0.
The dot product is 0, so they're orthogonal. Okay?
You can also, like,
So we're
kind
finding
of, you can kind of fact check them if you think about it.
Huh?
Like the way I did it, I just looked at it.
All right.